Hi there. In this video, I'm going to talk about time-based regression for carrying out geo-experiments. Time-based regression simply means that we also incorporate the value of the variable which we are predicting as one of its predictors. So it basically means that we use the same variable shifted in time as one of the input variables. That's pretty much all time-based regression means. You could have other variables as well in the regression model, but that's basically one of the factors. Now, there are obviously ways to do this manually by doing it from scratch, but there is also a way by using existing open source packages. So one of those packages is the matched markets package by Google. So what this does is it uses its internal processes to come up with matching of markets, meaning that you want to, obviously for geo experiments, you want to have test and control markets, but you need to have comparable markets. You cannot just compare apples with oranges. So match markets is a package which will choose the best set of markets which are most comparable from among all of your geos. These geos, of course, can be DMAs and designated geographical marketing areas and the usual ways to split them up. But which of those are most comparable given the data, historical data that you have, given all the other parameters? That's what match markets will do for you. And then of course you have to carry out your experiment, and then the post analysis, and finally your interpretation. So we'll go through all of that. So in this video I'm going to show you an implementation of this. So let's actually jump into this document here. So we'll just move between these two, the Google Docs and the Google Colab file. So in the Google Doc, we also already have a description of what this process involves. So first of all, to look at the bigger picture, we are designing a scientific test. That's the whole point. We want it to be backed by statistical and robust scientific methods. So we are trying to understand the question: if we are spending, suppose, an extra 300K on our advertising, suppose on a new channel, then will it give a positive return, or is it just money that I'm wasting, just burning cash? So you can't just look at sales when you increase spending. You will have to also find a scientific way, because it will already have some natural variations. And that's where controlled experiments come into the picture. And one of those happen to be geo experiments. So we are basically doing an incrementality testing here. We are testing for the incremental impact of this additional spend in advertising, and we are going to test it by applying this change in certain geos and comparing it with similar geos which are similar in other ways, except for that introduction of the new advertising. And that's basically what geo experiment does. So this is a scientific approach where we have test groups and control groups, and the difference in the outcomes between these two will give us the true impact of the additional ad spend. So now we'll actually go to the notebook and we'll see the implementation of this code. So now we are within the notebook, and this notebook, by the way, actually comes from Google's Match Market itself, which is given in the GitHub library. And there is a lot of code which is already available, so that's why it's open source. You can make use of this code, so you can not be a full-time data scientist also and still work with it, but you would need to know some stuff, why, what is being done, and stuff like that. So first of all, in this first cell here, we load libraries. This code is a little bit tweaked, by the way. It's slightly different, but yeah, you can try your hands with it. I'll share the Colab file. So first of all the important modules are being loaded. So as you can see, matplotlib and numpy and pandas, these are for visualization, these are for the data manipulation. And then you also have from scipy, you have imported stats to carry out some statistical tests and other manipulations using statistics. So first of all, you will have to provide two sheets with data. The first will be a sales data sheet. Another one will be a geo eligibility sheet. The sales data sheet will basically consist of the spends and and the sales and the spends and the sales for the different geos and dates. So let's actually look at these two one by one. So like I was saying, this is the first sheet that you have to provide. This is the sales data sheet, and here you have date, geo, response, and cost. And so for different dates, you'll see that we actually have 20 geos. So for different dates, for each of the geos, you already have the response is nothing but your sales in this case. In marketing science, we often refer to the outcome as response, and then you also have the spend for each of these geos on that specific date. So that is your first sheet, and then you also have to provide another input for geo eligibility. This basically means whether or not, all the geos may not necessarily be eligible to be included in the test. This could be because of business reasons. There might be constraints that you need to really keep running tests in some geos all the time, or rather keep spending money, or may not spend money there, or for any other n number of reasons. You could have exclusion criteria or inclusion criteria for different geos. So let's actually look at how that sheet looks like. So this is that simple sheet which consists of the different geos which are marked by the numbers 1 to 20, and you have we have the columns control, treatment. So whether or not they're control and whether or not they're treatment. So obviously the geos which are included in either control or treatment, and whether or not they're getting excluded. So you can see here a couple of them have been marked as getting excluded. But the point is that these, that's why we have ones here. So this is, by the way, this is a concept of eligibility. So ultimately, obviously, the design is going to find out which ones will go to the final design, which will be the outcome of this model, which will decide which ones go to control, which one goes to treatment. But these are the only ones you can see zeros here and ones here because they are getting excluded. um, but what we'll see is that we'll actually not use this for this specific case. We are using a dummy data to run this experiment, to sort of do this demonstration here. We are actually go ahead and give all the geos the eligibility to be included in control and treatment. So I'm back within the Google Colab now, and so once all the libraries have been launched, as you can see, have been imported from match markets. We are importing lots of things here, which are going to be useful. And we also, for compatibility, we have just loaded something here, which is again not really important for this understanding. um, but let's yeah so the eligibility thing is, like I was saying, so we'll basically get all values. We are going to bypass the eligibility criteria that was mentioned in the sheet, but that's just to make it simpler for analysis. That's all really. So this first part is just providing the input data, and we have 2380 rows of data altogether. Now comes the parameters part. So this is where, again, this is optimized for speed, meaning for this example I have just iteratively created an example which takes much less time, like it's almost instant. Sometimes this can take quite a bit depending on the number of geos, depending on other parameters like level of confidence and power levels. So power level is very universal, 80% statistical power, and your confidence level has been taken as 90% here, and your average order value is 1, um, and your minimum detectable IROS is 3. So these are some of the input parameters. Like experiment duration has been given as 4 weeks, again very common, like you have 4 weeks of data, and you can have experiment budget as this number here, 300,000, and you can provide some alternative budgets, because this is then going to be used by the model to try and understand which one is the best. It's going to do some iterative analysis of its own, and you can of course exclude some dates. These two will actually be optional. So you provide these inputs here in this part here. That's pretty much all that is there in it, and there are some other constraints and parameters that can be provided here, right? So uh, if you want to really provide like treatment share range, treatment geos range, but yeah, this is not so important for understanding. Most of these will be hard coded for you just to make things easier if you want to use it. And once that is done, you will have the parameters set here that we have just discussed. So as you can see, all eligible geos, because we have just bypassed the eligibility criteria for the geos, and the minimum correlation that we're going to go for. So this is basically a requirement for match markets. Like there has to be a correlation between the geos for them to become chosen for control and treatment, either of these. And that's because if they are not very highly correlated for the parameters that you're checking them for, then it is not a good idea. So in this case, as you saw in the sales data, we have spends and sales. These are the main criteria that we have chosen. Now, these are the possible designs. That's what's going to be estimated now by the next cell. And here we have something called a greedy search. So that's the methodology that's being used, a greedy search methodology. And you'll see that this is being invoked through the class. So that's what's giving us this instance here of MASH designs. And this is basically going to give us the research design that we're going to use. Ultimately, it's going to explore all the possible designs and then basically give a recommendation of which one among these is the most recommended design. So here again, there's not much you need to do. Most of these are just calculating different things like minimum detectable IROS, minimum detectable lift. So again, there needs to be a definition of what is the minimum detectable impact and the lift from it, because that's necessary for statistical analysis. So you will see that there are certain tests that are involved here as well, and those tests have to be passed. And for being approved as designs. So that's what pretty much this part here does. And you will have a selection of a design, and then um, you will finally ultimately get what design has been chosen. So one valid design, and you will see that after the greedy search has been done, um, again it just takes like less than a minute. Sometimes it can take more if you are if it involves a more complicated process of finding for the best version of it. Okay, best version among all the designs. So what is meant by designs really is what is going to be the budget, what is the minimum detectable ROAS, and what is the minimum detectable lift. And this is for the combination of how many treatment and control geos are included in that setup. So if you look at this one here, I'll just zoom in a little bit. These are the treatment geos here, control geos, and you can see treatment geos. So that's basically what it means. So like I was saying, so among all the 20, you will have some getting assigned as treatment, some getting assigned control, and you can see a very high correlation between them. This is very important because without that, you will not have a proper research design, or test design rather. So this is where you see that design one, so 6 scenarios have been created, but the best one is actually the one marked in green, because your minimum detectable IROS was actually set at 3. So this was the minimum one that you need to detect. Okay, and this is more than what we require. Or rather, I mean, it's not going to be able to detect. So the lower it goes, basically the harder it is. Okay, so that's how lift works. Like if ROAS or the absolute lift, if that becomes lower, it becomes harder to detect that, and therefore you need more budget. So you need more budget here, as you can see, to detect a lower IROS. This was our threshold, and that has already been met. So a minimum detectable lift in response is 1.55%, which is the same in all cases. The same split, so 3 geos excluded, 8 in treatment, 9 in control, and they all cover 41%. So basically 41% by the treatment group. So you have some left for control as well. This is basically the revenue from all your sales, from all your geos included. And this is how much the spend is corresponding to the baseline cells in response. So this, if this is very small, so you can see 0.52% is a small, so that you're not spending too much, and it's not having a disproportionate effect. But at the same time, if it is too high, then it's also a problem, because or if it is too low, then it's also a problem, because then you will not, it will just get drowned, and you will not get any understanding of the final effect. And so if this was scaled budget, if this was scaled nationally, so for instance this was at 41%. So if this was basically this test were to be implemented, like if you were to use this test in real implementation, you would basically go on to apply that at the at the budget level, and then you will ultimately spend, instead of 41%, you would spend 100%, which would mean 54k instead of your 20.2k. So that basically what this really means. So the design is complete here. This is the most important part. This is actually matched markets up to this point. After this really comes the design diagnostics and the match geo pair. So this is where the pairs are shown. This is where the baseline statistics are being shown here. So we are actually going to check the output of the same now. So you'll see that, again, these are the match markets. So you'll have, by matching simply means like which are control and which are geo, which are treatment, sorry. So these are, again, this is just a repetition of that, but we did carry out few tests here, like AA tests and the Brown Bridge test, right? So you'll see that there are certain scores, certain um, there are certain tests that we carried out, right? and and once those have actually been passed, you will get an output of this sort. So AA test is really for balance, Brownian bridge is for stability, and Durbin Watson for autocorrelation. Let's actually not go into the details for now among into all of these tests. I'm going to share more mathematical details about this in the near future. So but the autocorrelation is basically in the residual. So do follow me. I'm going to share more information on the mathematics and the analytic side of these tests. So the geo assignment details is like we have 20 geos. We use 10. We use 8 for treatment, 9 for control, and 3 were excluded. And in treatment group you can see, and control group you can see, these are the details, like what's the total sales from each of these groups, and the spends, and the historical rows. This is all from historical data. And then you have individual geo level statistics for each of these individuals. So these were the aggregate for each of these groups. And for quality minimum detectable effect, this is what we have got. Like this is the minimum effect that we need. This is the optimal target for budget. Remember, we saw it was something around 20k, and this was the revenue coverage. Now we basically go into the summary and results. This is after a post analysis. I mean, this is basically a post analysis. This is what has already been, after 4 weeks of test has been carried out. So you can see the design was used for 114 days. 5 days were excluded, right? And that's basically being used for cool down period after the test has been over. And so there you go, like 8 geos in treatment, 9 geos in control. We have seen all of these before, and these are the numbers, selected design, and again, these are numbers we have seen before. The important thing here is that this is our hypothesis, this is what we are testing for. We are testing for whether or not iROS is 0 versus, which is our null hypothesis, versus our alternative hypothesis, which is H1, which is it is greater than 3. So that's our minimum detectable incremental iROS, remember. And this means that at 90%, we are 90% confidence, we have 90% confidence that we won't falsely detect an effect when there is none, or 80% probability of detecting an effect if the true ROAS is greater than 30. So these are the implementation details, and we basically run this test, and then we see that all the analysis is complete. And so now that all the analysis is done, we actually uh, we do a simulation. So once again, another simulation has been done for the post test period, right? And so we have a cool down data as well, because we want to not just we don't want to just continue immediately after the test has been completed, basically. So we'll just show you what the post test analysis really looks like. This is where we actually calculate the iROS and the lift. Okay. And there is, you just need to run those cells one after the other. And this is where, like I was saying, so there is a cool down period, and for that cool down period where you will basically compare with during the test period, and the numbers between the test and the cool down period. So we are obviously, with respect to our thresholds, we are going to compare whether or not um, you know uh, the test has been successful, or whether it's simply not successful. So this is the TBR analysis. The point estimate here is 2.433. The precision is 0.162 at 80% confidence interval. This is the range that it will lie between 2.27 and 2.59, and the probability that it's greater than 0 is 100%. Okay, and incremental cost is 300,000, and incremental response is 740k, and relative lift is 20%, almost close to 20%, 19.18%. And this is the cool down period. This is without the cooldown period, and this is with the cooldown period. We have 2.855, and you can see that. So what this does is that we, if we do the analysis right after the test ends, we tend to lose out some additional impact that may just continue to have. So just because you stopped an ad now, like on the concept of ad stock, for instance, doesn't mean that the effect is over immediately. So it'll have an effect after a while as well, for a certain period, and that's what cooldown basically means. And you can see that the precision is 0.213. Again, follow my videos, I'm not going to explain. So the precision is a certain statistical meaning, but it's important, like how precise this is. And again, the probability is 100% in this case for the simulated data, and you have relative lift of 14.63% here. So here's the additional lift that came with the cooldown, 128k. So yeah, the difference is 0.422 between the cooldown and without cooldown for the incremental rows. And let's actually look at the visualization, not obviously going through the visualization code. That's just for visualizing the stuff, and this is the most important stuff, most interesting stuff, I'm sure, that you will find. Here we see the observed versus the counterfactual response, that is the sales. So this orange line here stands for the sales, which is the observed value. So you can see that the observed value after this point here, like this was the intervention point. As you can see, test start by this first black line. This is the test end by this second black line. And the counterfactual is given by the dotted blue line. So you can see that without the intervention, the sales numbers would have just carried on as given by the dotted blue line. But instead, it just had a massive shift here, the dramatic shift after the spend was increased by the amount we discussed earlier. Now, once the test is over, which is at this point after these 4 weeks, you can see exactly 1 month, it starts to dip a little bit, right? The lift starts to wear off. But we are doing the measurement, so you can see, but it still hasn't worn off entirely. It starts to do, but it starts to dip, but it still carries on. So the effect is still there, and that's why we have a cool down period here of 10 days. So this is that period where rather it's for 2 weeks actually. You can see from the 1st of November to the 15th of November. For this period, we are basically taking a cool down period. And you can see the point wise daily incremental lift. So you can see the lift is basically decreasing, right? But nonetheless, you still have lift, and you can see that. So this is for the entire test period, though, by the way. This is only starting from this date here, like 1st of October, and you can see that it starts dipping. That it goes into negative is not important. That's just a case of how the simulation has been done, and it's not usually going to be the case. But you can see 80% confidence interval. You have the shaded parts here. So as the test moved on, the confidence interval actually shrunk, which is great. Um, so so that's the point, like your daily difference up to the point where the test actually ended, which is somewhere around here. So you can see that after that the lift started dipping, and then you have the cumulative effect, which shows over time how the lift actually accumulated. And you have a visualization summary which gives you daily lift statistics, periodal breakdown, cumulative lift, final cumulative lift, stuff like that. So you basically get point estimates, 80% confidence interval, which shows you the range, the upper and the lower thresholds, the cumulative effect at the end of the test period, at the end of the cumulative period, cool down period. So we already saw that there's an additional lift here. You also have the the average lift per day, and then you have the minimum and the maximum daily lifts. So that's pretty much it. That's the total analysis here. Again, this was done on simulated data. What is important to note is that you really need to have good quality data to be fed into it. Otherwise, either the correlation threshold is not going to be met. So unless the correlation is high for the parameters you've chosen for the different geos, it's not going to work. It's actually going to throw an error and you will not be able to proceed. But the important thing is, like, don't just include stuff just for the sake of meeting a correlation criteria, because then you're going to end up with really poorly matched markets. And this is so important. Like, whether or not your test is successful is not just whether or not you are able to run through this. And you know as you can see, like, it's relatively easy to set the design up, and it's relatively easy to also run through the validation tests, and all the things are already pre-built, and you can also sort of go on to do a post-test analysis and see what kind of lift you get. But whether or not the lift calculation is correct depends on whether or not the markets were also properly chosen. So just one thing before we finish this off is that, remember from the the design that we had several budget recommendations, and we had like 16K, 20K. Remember, for 16K it was too conservative, because we were looking for uh, a better, like I said, like, you need more spend for lower detectable lift. So since the detected lift was more than 3, we wanted 3, and therefore we needed 20K, a little higher. So that was our optimal case. But 20K is usually a lot lesser. You will typically see that you might need slightly higher spending, and that's because the data was just a little too perfect in our simulation. Again, it's mentioned 100K to 300K. I'm certain that that's not the amount of budget you require for a test, but you will still need to actually figure out whether or not 20K is going to be enough. In many cases it might not be. You really have to do it case by case. Match markets is, I'll I can tell from my experience that it's going to be relatively more difficult to actually do it in real case. Like, it's much easier to implement, but you will really have to design it properly, and you have to do like, you really have to decide what parameters to include. That initial creation of the data sets, like, what data you would provide in the form of inputs, like the sales data and stuff, that's very crucial. So once again, regarding the test, the validation tests, I've previously received questions around this. So the Durbin Watson and Brown and Bridge are like tests. Apart from the A test one, the A test is obviously very easy. Like, you're just trying to see that you're running same thing parallelly twice, and you're just checking whether or not you're getting the same outputs, just to show that whether or not the groups are balanced, or whether or not there is anything internally within them which is problematic. But these two tests in particular, Durbin Watson is for testing whether or not the residuals are independent over time. So it ensures that standard errors are correct. And your Brown and Bridge test, it is basically about stability over time, the relationship. Otherwise, if the relationship, suppose the treatment group, the effect of the treatment, the increase in treatment group is far more in a certain period, whether in the pre-test or the post-test, then it just ensures that the counterfactual is valid or not. If it jumps too much, then you know that the relationship is broken, and your test may not just give the right kind of output. So your counterfactual has to be valid, because you need to understand whether or not it's going to keep following the same pattern that you've seen in the past. So, like I said, follow me for future posts. I can't stress on this enough. Follow me on LinkedIn, follow me here on YouTube, and you're going to get more information around this thing. So hopefully this was useful. This was the full implementation of your time-based regression based match markets open source package from Google. This is used for geo-experimentation. There are other methods for incrementality testing, other methods for geo-experimentation. I've spoken about those in the past. Do check out my channel. I'm going to link some of them in the YouTube description, as in the video description as well. But yeah, thanks for watching. And if you have any questions, do let me know in the comments. And I'll see you in the next one.